Okay, so this is part 3 of my pre-Tuesday videos. Sorry it's a little later than I intended, but this is the section that gives a, quote, closer look at heat capacity. Your previous exposures to heat capacity was mostly for use in calorimetry. Maybe you remember problems from General Chem where you would like heat up a piece of metal and put it in cold water and calculate the final temperature. You would need to know the heat capacity of the water and of the metal. In the lab, we mostly use heat capacity to look at, let's say, the delta H of a reaction, because you would measure how warm the water got or cold the water got, and then you would do some math to figure out how much energy the reaction gave off or took in. Here in PChem, we want to look more closely at the process to see how it will matter. So what are the conditions that will lead to different values of heat capacity? You've had a little bit of insight of this already. We discussed gases, for example. Depending on the nature of the gas molecule, atomic gases versus molecular gases, linear versus nonlinear, you could absorb more or less heat energy. We do suspect that it will matter how the energy transfer occurs, because think about our discussion of work. When we did an expansion against a constant pressure, you get a different answer for the work than if you do it in a reversible nature with lots of little steps. It ends up mattering if the container is insulated or not. In other words, can you have energy flow into the system to replace the energy that's lost doing the work? Let's just look at a little schematic here. So you're adding energy, heat energy to a substance. Now you know right off the bat, if you're going to add energy to a substance, you're going to increase the motion of the molecules in that substance. Doesn't matter if it's solid, liquid, or gas. However, you need to know a lot more information before you can calculate the final temperature. You need to know the amount of heat that was added, the amount of thermal energy that was added. You need to know the amount of substance that you're adding it to, because the moles of that substance will matter. You need to know the nature and the state of that system. We've already talked about how different gas molecules can absorb different amounts of heat. It matters if it's a solid, liquid, or gas, and you want to know the conditions of the process. So we've already given some insight to doing things in a constant pressure environment, in other words, out on a benchtop, or in a constant volume environment inside a bomb calorimeter. Is that going to affect what we're going to work on here? Well, that's what we're going to find out. So in general, if you have some kind of heat transfer, so we added heat energy to our system here, the amount of heat that gets transferred into the system is going to be exactly equivalent to what the heat capacity of that system is times the change in temperature. Usually heat capacities are in some amount of, let's say, joules per degree. And so if you know those two values, you can calculate the Q. Or if you know what the Q is, you could figure out what the heat capacity is by rearranging the equation. If you're dealing with a pure substance, you could speak of the molar heat capacity. That's the C with the bar above it. It's going to be the heat capacity of a specific sample divided by how many moles you have. Earlier in the book, I didn't make a big deal about it at the time. They talked about different properties as being extensive or intensive. A molar heat capacity is something that's intensive. It's solely dependent on the nature of the material, whereas heat capacity is extensive. How much you have is going to relate to how much heat the system will absorb. So what do I want to talk about next? Well, we've already seen that the change in the internal energy in the bomb calorimeter system is exactly equal to the heat that's generated in the system. So therefore, we could do a little substitution here and say that the constant volume heat capacity is going to be equal to the constant volume heat transfer divided by delta T. Okay? And that was going to be equal to delta U over T. In the constant pressure process, so that was constant volume, that was in the bomb. Constant pressure, that's another way of saying that's out on the benchtop. Remember when we defined changes in enthalpy not long ago? That's equal to QP. And so, therefore, it follows that I'm going to put a little bunch of lowercase p's into my equations here and generate some equations. So remember how we talked about the fact that the deltas refer to large amounts. If you talk about infinitesimal amounts, you might expect that we're going to be having some integrals in your life. And so if we change what we just did into infinitesimal changes, the little p is to remind you there that's a constant pressure. You could do some rearranging and get CP dt. How about that? And I could do the same for above too. So with infinitesimal changes, that's going to be the partial derivative of u with respect to t, constant v, or du is equal to cv dt. These are equations that you will see again. So what I've written out here is a derivation. It actually kind of reproduces what you've already seen, but I just wanted to make the statement that this is these differential forms end up being the most versatile, and I'll explain why right now. So if you want to get a value of a delta U for a real measurable quantity in lab, a delta U or a delta H, you have to take the integral, then, of the heat capacity times dt. Now, what I've written here is the derivation for when you can assume that the heat capacities are constant over the range that you're interested in. Constant over the T1 to T2 range. Our book says approximately within 50 degrees. As long as you're not changing states of the material, that's fine. If you do that, then you're just basically multiplying the heat capacities times delta T, or on a molar scale, you could do that. However, many studies show that a polynomial expression is probably better. So many studies over ranges of temperature lead to, for example, heat capacity, constant pressure, expanding that out to another term. So if you have a larger range, you may need to integrate a polynomial. And I suspect that in some future problem we'll do that. Yep, I found one a little later on. Okay. So now the constant volume and constant pressure heat capacities are generally the same if you're in the condensed phases. But for gases, Cp is larger than Cv. We went through an example, I think recently we were talking about the fact that adding energy to a system may be immediately used as work by expansion of the system. So let's say a heat added to a gas at constant pressure. Again, imagine a balloon out in normal pressure. Heat added to a gas at constant pressure will immediately do some work. As it gains thermal energy. So therefore, you need to add even more heat to achieve the same temperature. More heat to achieve same temp as constant volume case. Okay, so let me just make this clear. So I've got some gas molecules in this rigid container. If I add, I don't know, let's just say 50 joules of heat energy, depending on the heat capacity of the gas, it's going to make the temperature rise to some level. But the fact is, if I'm adding the same amount of heat to a balloon, I'm going to lose some to work. Because as the balloon expands, and I'm moving my hands, which you can't see, but as the balloon expands, you're not achieving the same kinetic energy of the molecules, so you need more energy to achieve the same level of temperature increase. So that's why that's true. So I have a little derivation here to look at this more closely, and let's see if I could make this guy shrink proportionally. Is that going to be possible? No. Let's move that up. Squeeze this in here. So let me use blue, and I'll make my pen a little bit bigger. Okay, here we go. So from the definition of enthalpy, which you saw earlier in the chapter, H was equal to U plus PV. Some of these derivations I just like. I think they're elegant, so that's why I want to show them too. So if enthalpy is internal energy plus PV, by definition, we're going to add the ideal gas law to this to make a substitution. Why do we do these things? So that'll give us neat things when we rearrange them. So that's a different version of enthalpy. Now, let's add an infinitesimal change. So we're going to add little d's everywhere. So d instead of deltas. So little change on the left is going to be equal to little change on the right. Since it's a sum, and n and r are constants, that's what that leads to. Now, we just came up with some definitions not long ago, right? So, where are Cp dt? That was on the previous page. Here we go. So I've got Cp dt. I've got this guy, Cv dt, plus nr dt. Aha, I could do some canceling. Cp equals Cv plus nr. Then Cp minus Cv equals nr. And the molar heat capacity at constant pressure minus that is equal to r. So we love when long equations turn into cute little short equations. All right. Now let's do a couple of examples, and I'm going to look for some problems for you to try. All right. Example 3.5. I'm going to heat some xenon, 55.40 grams worth, from 300 Kelvin to 400 Kelvin. Assume the ideal gas law. Calculate delta U and delta H. Okay? So xenon is a monoatomic gas. So we just have 3/2 R for the constant volume heat capacity. The constant pressure heat capacity is going to be 3/2 R plus R based on the derivation we did on the previous page. So this is going to be 12.47 joules per K dot mole, and this is going to be 20.79 joules per K dot mole. So delta U is going to be the number of moles times the constant volume heat capacity times delta T. So it turns out that 55.40 grams is 0.422 moles times 12.47 joules per K dot mole times 100 degrees Kelvin. That's 526 joules is the delta U. delta H is NCP dt, Cp bar dt, and that's going to be 0.422 moles times 20.79 joules per k dot mole times 100 K, 877 K. So I have a little note here. Note that the internal energy is less due to some of the energy being used up as work. So, right, just as I said before. So need to add more because some is lost as work. So as I gave you a little foreshadowing earlier, heat capacities are not always constant over ranges in temperature. For this problem, we've got 1.46 moles of oxygen gas, and we're heating it from 298 K to 367 K. That's actually a smaller temperature range than the previous problem. However, it is bigger than 50 degrees, and so we'll see what we have here. So let's calculate the delta H. Remember, that's the one that's attached to constant pressure or open atmosphere heat. So constant pressure heat transfer is enthalpy. So delta H is equal to the integral T1 to T2 of N Cp bar dt. And my range here, I've got 1.46 moles. Then I've got my polynomial, 25.7 plus 0.0130 over Kelvin times T, joules over K dot mole. Pull through the constants. So I pull through the 1.46 moles, and then I have to evaluate 25.7 T plus 0.0130 T squared over 2 K, evaluated from 367 down to 298. Oops, forgot my little parentheses in there, and I got my units too. All right, so where's my calculator? I'm not prepared. All right, so let me see here. I've got I'm going to leave my units out and be lazy. 146 times 25.7 times 367 plus 1.46 over 2 times 0.0130 367 squared, then minus the other term, 1.46 times 25.7 times 298, and I could do this, plus 1.46 times 0.0130, forgot my 2, got to throw my K in there for units, and then 298K. All right, so I didn't waste your time by doing the calculations, but I multiplied it all out. I just want to assure you that these units are joules, and I'm maybe a little sloppy with sig figs here. I included 4, but I got 3,023 joules. Just to convince you on units, because this is moles, T is going to be Kelvin, and then you've got this joules over K dot mole. So only the joules is surviving. If you look carefully through it, you'll see that that's what happens. Let's see. Yeah, that's why kind of that mysterious K has to go along for the ride. I think you can see that by doing this polynomial, you are adding kind of some correction terms that aren't as big. You'd get let me see, if you didn't have that second term and you just used a flat heat capacity, I'm doing 13,770 minus 11,182. You would have gotten 2588. So it's about a 20% error if you didn't use the polynomial. But that's example 3.6. And so finally, after having gone through this, please try, if you have some time, to do these problems 13, 19, 20, 21, and 25. I think I gave you 3 problems on the other one. So give a good shot to these. Please come to class with questions. I hope you're following along. I don't know if we should schedule some out-of-class office hours or something to do more problems, but I want to make sure you guys feel confident about this stuff before our next assessment. All right, I'll see you soon. Bye-bye.